Welcome, everyone. Today we're embarking on a journey from what's that to oh, that in the world of artificial intelligence and machine learning. You might be wondering, why am I here? Well, let me tell you, you're part of the Blissfully Unaware Club, and today's graduation day. That is if you don't know much about AI ML as of yet, but for those who know everything about AI ML already, this is not video for you. This is an AI ML introductory video. So there you go. By the end of this presentation, if you're interested to follow through, you'll be throwing around terms like neural networks and deep learning, like you're auditioning for a role in the Matrix 5, Revenge of the Algorithms. Now, I know what you're thinking. AI, isn't that just robots taking over the world? Well, not quite. It's more like teaching your computer to be as smart as your smartphone, which, let's face it, it's probably smarter than some people we know. We're going to demystify AI and ML, turning those question marks floating above your heads into light bulbs. And don't worry, we won't go so deep that you'll need a computer science degree to understand. This is a crash course, not a crash and burn course. So, buckle up, put your thinking caps on, or better yet, let the AI wear the thinking cap for you. We're about to turn your what's that confusion into oh, that comprehension. And who knows, by the end of this, you might even be able to explain AI to your grandmother, or at least your tech-savvy cat. Let's dive in and discover why AI is less about Terminator and more about terminating your confusion. This would be an exciting journey for us to get into the world of AI. In this first part of our adventure, we have an engaging lineup of topics that will give you a comprehensive introductory understanding of AI. This presentation has two parts. This is part one, and we have a separate video for part two. And this is the first one of a series of AI ML videos in PowerPoint format. We'll start with an overview of AI to set the stage, followed by a historical perspective of AI to see how far we've come. Then we'll explore AI paradigms and approaches, delve into machine learning fundamentals, and venture into the depths of deep learning and neural networks. Our journey continues with natural language processing, NLP in short, where we'll see how AI understands human language and computer vision, giving machines the ability to see. We'll also touch on robotics and AI, discovering how AI is revolutionizing robots. And finally, we'll address AI ethics and societal impact, exploring the responsibilities that come with AI advancements. This is just the beginning. We have part two, as a continuation of this presentation, where we'll dive even deeper into the topic of intelligent agents and some other AI topics. We'll talk about them from an overview perspective. I hope you join us for part two as well to complete this AI introductory journey into the world of AI. Let's get started. Imagine a world where machines can think, learn, and adapt just like humans. This is the realm of AI, where we explore how computers can perform tasks that typically require human intelligence. First off, what exactly is AI anyways? Well, it's like teaching a computer to be a know-it-all, but in a good way. We're talking about machines that can reason, learn, perceive, and understand language. Basically everything your teenager claims they can do, but actually does. Let's time travel through AI history a little bit, shall we? Picture this. It's 1950 and Alan Turing is playing Guess Who with computers. Fast forward to 1956, and a bunch of smarty pants at Dartmouth decide to call this whole shebang artificial intelligence. Then we hit the AI winters, so-called AI winters. Turns out teaching machines to be smart is harder than teaching cats to fetch. But like any good Hollywood comeback story, AI bounces back, and by 2012, it's recognizing images better than your grandmother recognizes her favorite soap opera characters. Now, where are we? Well, we've got narrow AI that's really good at specific tasks, like beating humans at chess or recommending movies you'll probably fall asleep to. It's infiltrating everything from healthcare, because Dr. Robot doesn't need coffee breaks, to finance, because who doesn't want a computer managing their life savings, and even driving cars. No more blaming the GPS for getting lost. But hold on to your hats, because the future of AI is both exciting and slightly terrifying. We're talking about artificial general intelligence. Imagine if Siri, Alexa, and your smart fridge had a super intelligent baby. Of course, with great power comes great responsibility. Thanks, Spider-Man. So we're also tackling the ethical stuff. We're making sure AI doesn't become biased, because we have enough of that from humans. Thank you very much. Doesn't invade privacy more than your nosy neighbor, and doesn't take all your jobs. Although, let's be honest, who wouldn't mind a robot doing their taxes? So there you have it. AI in a nutshell. It's come a long way from sci-fi dreams to, hey Alexa, order more toilet paper for me. Stick around, because this ride is just getting started, and trust me, it's going to be smarter than the average bear or human. Now let's take a journey back in time to uncover the milestones that have shaped the evolution of AI. From early theoretical concepts to modern-day breakthroughs, the history of AI is both fascinating and enlightening. We kick off in the swinging 50s with a logic theorist and general problem solver. These early AI programs were like the Elvis of the computer world. Groundbreaking. The logic theorist was proving theorems while most calculators were still learning to add. And the general problem solver introduced us to problem spaces and heuristic search. It was basically playing hide and seek with solutions. Fast forward to the groovy 70s and 80s, and we hit the expert systems era. MyCin, M-Y-C-I-N, it's an acronym, was diagnosing blood infections faster than you can say the word antibiotics, quote unquote. While Dendrel, also an acronym, was identifying organic compounds like a chemist after too much coffee. But these systems had their limitations. They were about as flexible as a Rubik's cube made of concrete. They couldn't learn, which is ironic for something called intelligent, quote unquote. The 80s and 90s brought us the neural network revival, not to be confused with the disco revival, thank goodness. We got Hopfield networks and back propagation, which sounds like a bad back condition, but was actually pretty cool. NetTalk was converting text to speech, probably sounding like a robot with a cold. But our AI friends faced some challenges. Vanishing gradients, like your motivation on a Monday morning, and limited computing power. Imagine running or trying to run Cyberpunk 2077 on a calculator. It's pretty impossible. Now we've arrived at the deep learning revolution. It's like the AI world suddenly hit puberty and had a massive growth spurt. Thanks to big data, because apparently size does matter here, improved algorithms, and GPUs more powerful than a rocket ship. We're seeing some mind-blowing stuff. AlexNet crashed onto the scene in 2012, recognizing images better than your grandmother recognizes her grandkids. Word2Vec in 2013 made natural language processing so advanced it probably understands Shakespeare better than your high school English teacher. And let's not forget AlphaGo in 2016, which beat the world champion at Go, making us all feel a little less smug about our board game skills. So again, there you have it, the historical highlight reel of AI. We've gone from basic problem solving to systems that can probably beat you at chess while writing a symphony. The future is so bright, we're gonna have to wear shades, or maybe VR goggles. Next, we'll have a whirlwind tour of AI paradigms and approaches. It's like a buffet of rain-inspired computing, and trust me, it's more exciting than it sounds. First up, we have symbolic AI, the granddaddy of AI. This old-timer believes in spelling things out, kind of like your dad trying to explain how to use a smartphone. It's all about explicit knowledge representation and reasoning using rule-based systems and logic programming. Remember SHRDLU from 1968 to 1970? Probably not, since you're likely way too young to remember. Even I don't remember that. I don't know what SHRDLU actually stands for, but it is an early natural language understanding computer program developed at MIT. It was designed to simulate understanding of natural language within a micro world of simple geometric shapes. I know it was initially developed in Lisp, which is a programming language. It was like the world's smartest toddler, understanding natural language in a block world. Put the red block on the blue block, and voila, no tantrums involved. Next, we have statistical AI. The cool uncle who's always talking about probabilistics, and learning from past mistakes. This approach handles uncertainty better than a weather forecaster and learns from data like a gossip at a cocktail party. The poster child? Netflix recommendation system. We might all have used this. Netflix recommendation system is the reason you ended up binge watching that obscure Danish crime drama at 3 a.m. in the morning. Then there's symbolic AI, the rebellious teenager of the family. It's all about neural networks and deep learning representations directly from raw data like a sponge on steroids. Remember AlexNet in 2012. Again, you may not remember any of this, but no worries. AlexNet burst onto the scene recognizing images better than anyone that I could think of. It was actually an aha moment that made everyone sit up and take notice. Last but not least, we have the hybrid approaches, the overachievers of the AI world. They're like that friend who's good at everything, annoying but impressive. These approaches combine the strengths of multiple paradigms like neuro-symbolic AI, which is trying to get neural networks and symbolic reasoning to play nice together. It's aiming for the holy grail, both learning capability and interoperability. In other words, an AI that can learn like a whiz and explain itself like a patient teacher. The paradigm parade, there you have it, from rule-loving granddaddies to data crunching teenagers. We've got it all. As we march forward in AI, understanding these approaches is key. Who knows? Maybe one day we'll have an AI that can do it all. I have no doubt they can one day. Solve complex problems, learn from its mistakes, recognize cat videos, and explain why it did what it did. Now, wouldn't that be something? At the heart of AI lies machine learning, a powerful set of techniques that enable computers to learn from data. We'll dive into the basics and discover how machine learning models are trained to make predictions and decisions. We'll take a roller coaster ride through the theme park of smart algorithms. First stop, types of machine learning. We've got three main attractions here. You might already have heard these terms being thrown around all the time, and they should not be strangers. One is supervised learning, the helicopter parent of ML. It's always labeling things, like a mom writing names on kids' clothes or lunch boxes before summer camp. Think spam email detection, teaching machines the difference between that Nigerian prince and your actual long-lost relative. The second attraction is unsupervised learning, the free spirit hippie of the bunch. It looks at data and says, labels? We don't need no stinking labels. It's like letting a toddler loose in a toy store and seeing what patterns emerge. That's unsupervised learning. The third is reinforcement learning. This is like the tiger mom of ML. It's all about reward and punishment. Imagine teaching a dog to fetch, but instead of a dog, it's AlphaGo, becoming a Go champion and making humans question their life choices. Now let's peek into the toolbox of key algorithms. For supervised learning, we've got decision trees. This is one of the key algorithms for when you can't decide what you want to have for dinner. SVMs, which is short for super valuable machines. What else? And neural networks, because who doesn't want to recreate a brain in silicon? For unsupervised learning, we have unsupervised learning tool or algorithm called k-means clustering, for when you want to sort your socks but can't be bothered to match them. And PCA, which is the acronym for Pretty Cool Analysis, if you ask me. Reinforcement learning flexes with Q-learning and policy gradient methods, which sounds something out of a spy movie, but those are tools we can use to implement these three different kinds of learning as machine models. Now, you want to get deeper into these terms, all information is at your fingertips, as I always said. Just Google them or wait for my upcoming videos, which will be doing deep dives into some of these concepts. This presentation here is just for introduction to AI. All right, next up, feature engineering. It's just like a data chef. Feature selection, picking the perfect ingredients for your machine learning recipe. Dimension reduction, when your data is more bloated than you after Thanksgiving dinner. Data transformation, turning data pumpkins into data carriages. These are analogies, hopefully can help you to sort of remember some of these. But, well, last but not least, model evaluation, because even machines need report cards. Cross-validation, the machine learning equivalent of quote-unquote check your work. Performance matrix, it's about accuracy, how often you hit the bullseye. Precision, how often you cry wolf and there's actually a wolf. Recall, how many wolves you caught. And F1-score, for when you can't decide between precision and recall, so you smush them together. Remember, machine learning is an iterative process. It's like trying to get the perfect Instagram photo. Adjust, filter, evaluate, repeat. And voila, you've got yourself a model smarter than the average bear, or at least smart enough to tell a bear from a large dog in a furry coat. As we wrap up this whirlwind tour, just remember, machine learning is reshaping our world faster than you can say the term artificial intelligence. From diagnosing diseases to driving cars, it's everywhere. So next time your phone finishes your sentences for you or your car parks itself, give a little nod to the magical world of machine learning. Now enter the world of deep learning, where neural networks with multiple layers mimic the human brain's ability to process information. This section will unravel how deep learning models power some of the most advanced AI applications today. Let's start with our star performers, neural network fundamentals. Picture a bunch of artificial neurons, like tiny silicon brains, linked up in a digital conga line. They're passing data like hot potatoes through activation functions, turning your inputs into outputs faster than you can say the word quote unquote backpropagation. Speaking of which, backpropagation and gradient descent are the strict coaches, think of it that way, making sure our neural acrobats don't fall off the high wire of overfitting. Now let's meet our troupe of neural network celebrities. Number one is convolutional neural networks, CNNs in short. The prima donnas of the image world. They're so good at recognizing pictures they could probably spot Waldo in a split second. The second celebrity here is called recurrent neural networks, RNNs, and LSTMs, which is an acronym for long short-term memory. It's a recurrent neural network architecture widely used in deep learning. These are memory wizards. They're like that friend who remembers every embarrassing you've ever done, but for useful stuff. Transformer architectures, the new kids on the block, showing off with their attention mechanisms. They're so good at language tasks, they might start correcting your grammar soon. Now for some deep learning magic tricks that'll make your jaw drop. In 2012, ImageNet competition saw AlexNet pull a rabbit out of hat, leaving traditional computer vision techniques in the dust. 2016, which we mentioned earlier already, brought us AlphaGo, which beat the world Go champion. It's like teaching a computer to win at 4D chess, underwater, blindfolded. And let's not forget the GPT series, writing prose so well it might put Shakespeare out of a job. But wait, it's not all standing ovations and rose petals. Our deep learning circus faces some challenges. First challenge would be explainability. These models are like teenagers, complex and hard to understand. We're working on making them more transparent, but it's like trying to get a cat to explain its behavior, and it's going to take some time. Data requirements. These models are data gluttons. They need more examples than a toddler needs to hear no before understanding it. Adversarial attacks. Turns out you can fool these smart models with carefully crafted inputs. It's like tricking a self-driving car with a carefully placed stop sign that says go in very tiny letters. Energy efficiency. Training these models uses more energy than a small country. We're working on a diet plan, but it's a work in progress. Again, it will take some time. But fear not, our AI ringmasters are hard at work developing new tricks like few shot learning. What's that? That is like teaching a dog new tricks with fewer treats and making models more interpretable, like adding subtitles to your cat's mouse. So this is sort of a thing that we call the deep learning circus. It's pushing the boundaries of AI faster than a neural network can say, quote unquote, tensor. Who knows? Maybe one day these models will be so smart they will be explaining themselves to us. And actually, this is kind of what they are already doing today. Now, I want you to imagine, now take a minute to imagine a computer that understands and responds to human language. That is the magic of natural language processing, NLP in short. We'll explore how NLP enables machines to interpret, generate, and interact using human language. Let's start with our main attractions, the NLP tasks and applications. Sentiment analysis. This is about teaching computers to understand emotions, because sometimes even humans can't tell if the text from your boss is passive aggressive. Machine translation, turning omelette de fromage into cheese omelette. Don't know if I pronounced that correctly, but you know what I mean. Faster than you can say bon appetit. Question answering, like having a know-it-all friend, but without the eye rolls. Text summarization, for when you need to read War and Peace, but only have time for a tweet. Named entity recognition, helping computers understand that apple is not always a fruit, much to the confusion of health-conscious AI. Now, let's take a stroll down memory lane with the evolution of NLP approaches. I think that'd be fun. We had rule-based systems for quite some time now, the strict grammar teachers of the AI world. Statistical models, when we decided to play the numbers game with n-grams, n-grams. N-grams, for those who may not know, is a sequence tagging technique. N-gram is the sequence of words by which you want to tokenize the next. N is a stand-in for number, so you can replace it with the value you need. Look up the technique to find out more details if interested. Same with what I'm going to mention next, the acronym HMMs, which stands for Hidden Markov Models, and CRFs, short for Conditional Random Fields. All these acronyms belong to the family of graphical models in machine learning. It's like trying to understand language by counting words. Surprisingly effective, but not exactly Shakespeare. Neural network-based approaches. When we decided to mimic the brain and things got scary good. Speaking of neural networks, let's meet our neural NLP models. Word embeddings. Turning words into numbers is like giving each word its own set of coordinates in the language universe. Sequence-to-sequence models, the AI equivalent of, I heard you like sequences, so I put a sequence in your sequence. Attention mechanisms, teaching AI to focus, something we humans still struggle with. Transformer architectures, the cool kids on the block, BERT and GPT. These are the arguably two most popular language models to date. BERT, B-E-R-T, is the acronym for, or it's the short acronym for bidirectional encoder representations from transformers. Quite a mouthful. Developed by Google AI. It's a pre-training language representation model that fine-tunes NLP applications created by Google in 2018. Unlike other NLP models that use unidirectional attention flow, BERT uses bidirectional flow, which allows it to use context from both directions during processing. Now, GPT, you know GPT, it's used to like, everybody knows GPT now, I guess, stands for Generative Pre-trained Transformer, developed by OpenAI. It uses a unidirectional approach to pre-train by predicting the next token in a sequence, focusing on so-called generative tasks. So you can look them up more with more information if interested. Information is everywhere on the internet. Now for our grand finale, recent advancements. Few shot and zero shot learning. That is about teaching AI to learn like a human toddler, fast and with minimal examples. Except the AI doesn't throw tantrums yet. Multilingual models, because why speak one language when we can speak them all? Multimodal NLP, combining text with images and speech, is like giving AI synesthesia, but useful. Remember, as impressive as these language models are, they're still prone to mistakes. They might write a Shakespearean sonnet 1 minute and confuse some simple pronouns next. But hey, that sounds pretty human to me. At any rate, this is NLP in a nutshell. We've come a long way from hello world to AI that can write your emails for you. Just remember, if an AI offers to write your wedding vows, I would definitely double check those before the big day. Computer vision is this magical world where we teach machines to see, and sometimes they end up seeing things we wish they hadn't. Step into the realm of computer vision where machines gain the ability to see and interpret the visual world. This section covers how AI can analyze images and videos to recognize objects, faces, and even emotions. Excuse me. Let's start with the foundations of image processing. The equivalent of giving our AI eyes some fancy glasses. Image filtering and enhancement, because even AI deserves a good Instagram filter. Edge detection and feature extraction, teaching computers to appreciate the finer points of an image, like finding Waldo without human help. Traditional algorithms like SIFT, S-I-F-T, and SURF, S-U-R-F. The GOs of computer vision. GOs is short for original gangsters. The original gangsters of computer vision before neural networks crashed the party. SIFT, S-I-F-T, which stands for Scale Invariant Feature Transform, is an algorithm used to detect and describe local features in images. SURF, S-U-R-F, stands for Speeded Up Robust Features. SURF is a faster alternative to SIFT for feature detection and description. So I won't say more about these two features. You can look them up if you want, or wait for my other videos. Now let's move on to object detection and recognition, or as I like to call it, teaching AI to play the most advanced I Spy game ever. Our CNN family, the overarching family of algorithms that keeps getting faster and smarter. It's like the Kardashians, but useful. Single shot detections like YOLO and SSD, because sometimes you really do only need to look once. Why did I say that? Well, single shot detectors are a class of object detection algorithms that detect objects in images in a single forward pass of the network, making them efficient and suitable for real-time applications. Two prominent examples of single-shot detectors are YOLO, YOLO, and SSD. YOLO is a short acronym for You Only Look Once. SSD is acronym for Single Shot Multi-Box Detector, Single Shot Detector. These are the speed demons of object detection, perfect for when you need to know what that blurry thing in your rearview mirror is, like right now. Next up, semantic segmentation, or teaching computers to color inside the lines. Fully convolutional networks, FCN, turning classification nets into dense prediction machines. It's like giving your image classifier a paint by numbers kit. UNet and Deep Lab architectures. The cool kids in medical imaging and satellite analysis. They're so good at coloring, they make preschoolers look like amateurs. And for our grand finale, advanced CV, computer vision tasks, where things get weird and wonderful. Generated models like GANs and VAEs. That is about teaching computers to dream, and sometimes those dreams are indistinguishable from reality. It's all fun and games until your AI starts generating pictures of cats with human faces. GANs is short for Generative Adversarial Networks. GANs are used to generate new data samples that are similar to a given dataset. VAEs, variational autoencoders. VAEs are used for generating new data samples and learning latent representations of data. Image-to-image translation, for when you want to know what you'd look like as a Renaissance painting or your cat as a dog. Identity crisis, anyone? 3D computer vision and depth estimation, because the world isn't flat, no matter what some people on the internet say. Again, remember, as impressive as these computer vision models are, they can still be fooled. They might correctly identify 1,000 objects in an image, then insist that the fire hydrant is actually a small red giraffe. But hey, we all make mistakes, right? So computer vision in a snapshot, we've come a long way from does this grainy image contain a cat or not, to here's a photorealistic image of a cat that never existed. Just remember, the next time you think you're being watched, you probably are. But it's probably just a really enthusiastic AI practicing its object detection skills. Robots and AI. Picture robots equipped with intelligent brains. A bit scary. Capable of perceiving, learning, and interacting with their environment. Robotics and AI are transforming industries from manufacturing to healthcare and beyond. Let's dive into the fascinating intersection of AI and robotics. Robot perception and navigation. To navigate the world, robots need to see, understand, and remember their surroundings. This is where sensor fusion comes into play, combining data from cameras, LiDAR, and tactile sensors. With computer vision, robots can recognize objects, avoid obstacles, and make sense of complex scenes. One of the coolest tricks up their sleeves is simultaneous localization and mapping, SLAM in short. Imagine a robot being a cartographer and an explorer at the same time, mapping out an unknown area where keeping track of its own location, Think of it as the robot's version of multitasking. And it's crucial for environments where GPS just won't cut it, like indoors or on Mars. Planning and control. Once a robot knows where it is, it needs to figure out where to go and how to get there without bumping into things. Motion planning algorithms like rapidly exploring random trees, RRT in short, and probabilistic roadmaps, PRM in short, help robots chart a collision-free course in complex environments. But planning is just half the battle. Executing these plans smoothly, especially when unexpected things happen, requires advanced control systems. Techniques like model predictive control, MPC in short, and adaptive control ensure our robotic friends stay on track, even when the real world throws them a curveball. Robot learning. Robots are also learning to learn. Reinforcement learning, RL, lets them figure out the best actions by trial and error, much like how we learn to ride a bike. A prime example is OpenAI's Dactyl, Dactyl, which taught a robotic hand to manipulate a cube with impressive dexterity, showcasing RL's potential in mastering fine motor skills. Imitation learning, where robots learn by watching humans, makes programming them as simple as showing them how it's done. And with transfer learning, robots can train in simulations, think virtual worlds, and then apply what they've learned to the real world with minimal tweaks. It's like sending them to a virtual boot camp before field deployment. Human-robot interaction. As robots step out of factories and into our daily lives, they need to play nice with humans. Collaborative robots, or we call them cobots, are designed to work safely alongside us, using advanced sensors to detect our presence and act accordingly. Wait a minute, how do you know I'm not a robot or a cobot? Maybe I am. Anyways, social robotics aims to make interactions with robots as natural as chatting with a friend. Take SoftBank's Pepper, for example. You've heard of Pepper. Google it if you have not. It's SoftBank's Pepper. It can understand and respond to human emotions, making customer service interactions more engaging. Natural language and gesture interfaces are also evolving quite rapidly, aiming to make communicating with robots as easy as talking to your favorite virtual assistant. Challenges and future directions. Despite their impressive capabilities, robots still face significant challenges. Dexterous manipulation. Robots excel at repetitive tasks but struggle with the flexible, dexterous manipulation we humans find easy. Enhancing this could revolutionize industries like manufacturing and healthcare. Locomotion in unstructured environments. Most robots are used to controlled settings. Making them navigate unpredictable terrains like disaster zones or your cluttered living room is a major hurdle. Long-term autonomy and adaptability. For robots to be truly useful, they need to operate independently for long periods, adapting to changing environments and tasks. This is crucial for space exploration and long-term assistance. Sample efficiency in learning. While reinforcement learning has made strides, it often needs vast amounts of data. Improving this efficiency is key to practical robot learning. Ethical and social implications. As robots become more integrated into society, addressing ethical concerns and ensuring responsible development is paramount. Looking forward, we're on the cusp of seeing even more sophisticated AI and robotics integration. Advances in neuromorphic computing and quantum AI could produce more powerful and efficient robotic brains. Soft robotics and bio-inspired designs might lead to more adaptable and safer robots. As these technologies evolve, pardon me, robots will increasingly take on complex roles, from healthcare assistants to interplanetary explorers. The field of robotics AI is buzzing with potential, poised to transform our world in unimaginable ways. As we continue to innovate, the dream of creating truly intelligent, versatile robots is becoming a reality. As we delve into this fascinating world of AI ethics and societal impact, let's keep in mind that while AI can do amazing things, it also brings a few challenges that we must address thoughtfully. With great power comes great responsibility. The ethical and societal implications of AI are profound. And this section delves into the challenges and considerations of deploying AI responsibly. Bias and fairness. AI systems, like humans, can sometimes be a bit biased. These biases can sneak in through training data, algorithm design, or deployment contexts. For example, if a facial recognition system is trained mostly on images of light-skinned individuals, it might struggle with darker-skinned faces. We call this training data bias. To combat bias, we use fairness matrix. Demographic parity ensures predictions are independent of protected attributes. Equal opportunity requires equal true positive rates across groups. Equalized odds balances true positive and false positive rates across groups. However, it's impossible to satisfy all fairness criteria simultaneously, leading to trade-offs. Let's not forget Amazon's AI recruiting tool, which showed bias against women because it was trained on resumes mostly from men. Talk about a learning curve. Mitigating bias involves using diverse and representative training data, applying regularization techniques to reduce reliance on sensitive attributes, implementing post-processing methods to adjust model outputs, and employing adversarial debiasing during training. Okay, privacy and data protection. AI loves data, but with great data comes great responsibility. Key privacy concerns include data collection and consent, ensuring users know how their data will be used, data security, protecting datasets from cyber attacks, inference attacks, preventing AI models from revealing sensitive information. To safeguard privacy, we use differential privacy, adds noise to data to protect individual identities. Federated learning trains models on decentralized data, keeping it on users' devices. Homomorphic encryption allows computation on encrypted data. Legal frameworks like GDPR, you know GDPR already, which is just short for General Data Protection Regulation, which is implemented in the EU, and CCPA, California Consumer Privacy Act, a privacy law enacted in the state of California. These are just two legal frameworks as examples. They set the stage for data protection, giving users rights like data portability and the right to be forgotten. A round of applause for privacy, please. Next is AI safety and alignment. Ensuring AI systems are safe and aligned with human values is crucial. We address both short-term and long-term concerns. Short-term safety focuses on robustness to adversarial attacks, safe exploration in reinforcement learning, and making AI decisions interpretable. Long-term risks include the control problem. keeping AI under human control and value alignment, making sure AI respects human values. Techniques to align AI with human values include inverse reinforcement learning, infers human preferences from behavior; reward modeling, learns reward functions from human feedback; debate, trains AI to argue for and against actions with humans judging and debate and judging the debate. Organizations like OpenAI and DeepMind are at the forefront of this research, ensuring that AI systems do what they want them to do. Now let's talk about economic and social implications. AI is reshaping our economy and safety, bringing both opportunities and challenges. Job displacement and creation. While AI might automate some jobs, it also creates new ones. A 2013 Oxford study estimated 47% of US jobs are at high risk of automation. But history shows technological advancements often lead to new job categories. So don't worry too much. Skill gaps and reskilling. As AI changes job demands, there's a growing need for AI-related technical skills and unique human skills like critical thinking and emotional intelligence. Initiatives like Amazon's Upskilling 2025 aim to retrain workers for high-tech roles. Economic restructuring. AI might necessitate changes to our economic structures. Ideas like universal basic income, UBI, have been proposed to address job displacement. And there's a push for education systems to emphasize lifelong learning. As AI continues to advance, addressing these ethical and societal changes will be crucial. This requires ongoing collaboration between AI researchers, ethicists, policymakers, and the broader public to ensure that AI development aligns with human values and benefits society as a whole. So let's march forward, balancing excitement with responsibility as we navigate the ethical landscape of AI together. All right, now we're coming to an end. This slide has some, not all actually, some reference materials that I used when I'm researching for this presentation. Please feel free to freeze the video here if you want to take a look at this list. And this is the end of part 1 of this presentation. I hope to see you in part 2. Thank you very much for watching.